Hello and welcome to video 5 of the integration video series. We're going to now look at the area enclosed by the x-axis, more particularly having a look at it in graph form. Okay, here's a graph. It's an upside down parabola, perhaps something with a minus x squared in it somewhere. Let's consider that we've got an x value, an x-intercept of 0 and maybe 4 here. So what that looks like in integration terms is the integral of a certain function between the x values of 4 and 0 dx. So when we integrate that will find this area here, and there'll be no dramas there because the area under the curve is the shaded bit there. So that'll get us a sensible answer for the integral between 0 and 4. Things get a little trickier though when you've got an area between the curve and the x-axis that looks like it's under the x-axis for the whole time. So we might have an x-intercept of 0 and 4 here. What we'll have to do though to get our answer here is our area will have to be the absolute value of the integral between 4 and 0 of this particular function, because otherwise we'd get, I guess, a negative area. So this is the area we're trying to find in green here, the area between the curve and the x-axis, but we would get a negative answer there if we did all the algebra properly. So we'll have to take the absolute value, in other words, turn any negative values into positive values to make sense of that area enclosed by the x-axis and the curve in this particular case. Okay, here we have what we call an even function. We learned about even functions in the preliminary course. It's an even function. Now, part of an even function is that it's symmetrical about the y-axis here. So this area here, area 1, will equal this area over here, area 2. So what we can do, if we know it's an even function, and this might be something along the lines of y equals x squared, our function here, or another way of saying that, f of x equals x squared. What we know is if it's symmetrical, what we can find is just area 2 between, say, x equals 0 and x equals 4 there, and double it. So our overall area will be the integral between 4 and 0 of x squared dx multiplied by 2. Why is it multiplied by 2? Because you've got an area here and the same size area there. So the whole area, to get the total, I suppose we could put in here the area between 4 and minus 4 of x squared dx will actually be the area between 0 and 4, this bit here, and doubled. So that's if we have an x-intercept of minus 4 over there. So with even functions, we're allowed to kind of work out the area of half of it between the curve and the x-axis, and then just double it because we've got the same size area on the other side. Okay, slightly different one here. We've got perhaps a function of y equals x cubed, or f of x equal to x cubed. So it's our cubic. Now this is an odd function. If we remember back to our preliminary methods, it's an odd function. So what we can do here is, if we find area 1 and area 2, we'll have to do something pretty special here. So let's suggest that this is a minus 3 perhaps. That's a 0 and that's a 3. So what we'll have to do is if we work out this function between minus 3 and 0 here, we'll get a negative answer there. That'll be the same sort of size as the positive answer we'll get in area 2. So if we added those two together, just straight out, we'd get a total area of 0, because they're the same size as each other, so if we subtracted them, we'd get 0. So what we have to do is, we have to find the integral, our total area will have to be the absolute value of area 1 plus area 2. So even though this area 1 will give us a negative result, we'll have to absolute value it to make it a positive, and then add it to our area 2. Otherwise we'll get a really incomprehensible final answer of 0 for our total area there. So in this case, our total area, to be more precise about it, will be the absolute value of the integral of x cubed dx between 0 and minus 3, absolute value of that, plus just the normal integral between 3 and 0 of x cubed dx. Moving on. Now this is a pretty interesting curve we've got here, but it's another example of an even function. And we've got different sections here. But let's say we've got the x-intercepts of 0, 2, and maybe 5, and minus 2 and minus 5 here. To get the total green area here, I guess, because it's an even function, we know it's symmetrical around the y-axis. So let's just concentrate on one side, perhaps this right-hand side, and then we'll double our result because we've got the same sort of size areas on the left-hand side. So if we're calling that area 1 this time and this area 2, what we'll have to do, because area 2 is underneath the curve, we'll have to absolute value that. So the total area here, total area will equal area 1 plus the absolute value of area 2. So to be more precise, our area under the curve will be the integral of this particular function between 2 and 0, and because that's above the curve, we can just take the straight out result of that, plus the absolute value of the integral between 5 and 2 of the function, because that section would have given us a minus result. So we've got to be careful to, anytime we might get a minus result, then we have to take the absolute value of it. Now this section that I've written out here, I'll put a big box around here, that's only talking about area 1 and area 2 on the right hand side. Let's not forget we have area 3 and area 4 to contend with. Whoops, area 4. They are the same size on the left hand side of the y-axis as we have on the right hand side of the y-axis. So we can take what I've done in the box here and just multiply that by 2 for our total area. So matter of fact, up here I could have put that in brackets and times that by 2 as well, just to make sure. So I'm really concentrating on this right hand side, getting that right, and trusting that it's because I'm told it's an even function, that we can just double it for the total area in green there. Okay, hope that helps. So that's about it. Thanks for listening for that.